In the last video, I talked about how when a current increases, or how when we apply a voltage to a coil with very low or zero ohm resistance, the changing flux would produce an EMF that just balances the incoming voltage. Let me take this as a starting point to explain how this leads to the transformer action. Okay, so I would just summarize the main conditions from the last video. I have 0 ohm. I'm assuming 0 ohm resistance, and it's perfectly conducting, and I have a 1 volt input here, 1 volt input, and this goes from 0 to 0.1 ampere, and it happens in a time t of this change happens in a time t of, write it somewhere down here, 0.001 seconds. There is also this cross-section of area, say 10 cm squared. Okay, and the magnetic flux density as current goes from 0 to 0.1 ampere goes from 0 to 0.001 Tesla. Okay, so that's the situation, and when this magnetic flux increases, the conclusion from the last video was that it would produce an EMF that opposes the incoming current, and this opposing EMF must be exactly equal to the incoming EMF, which is 1 volt. So let's look at what happens now if we have a secondary coil. So let me just write this, remind ourselves that we're talking about the primary. This is supposed to act as the primary coil of the transformer. Let me now add in the secondary coil. Okay. So let's say I have another coil down here. Goes around here. Okay, I'm going to wrap this directly around the primary coil. So this arrangement would look a bit different from the picture we normally see of a transformer, which usually have a rectangular piece of iron with the primary coil on one side and the secondary coil on the other side. Now, the reason why I can't do that now yet is because you need that that rectangular piece of iron, or maybe circular piece of iron ring, to conduct, in a sense, or direct the magnetic flux to the other coil. Now since I don't have that, since I'm just looking at air at the moment, the magnetic flux, once it goes out of the coil, will just spread out and becomes very weak, right? It's not directed to another place. So I need to, for my secondary coil, just coil it around the first coil, okay, so that the magnetic flux would that is generated by the primary coil would also go through the secondary coil. So this is my secondary coil. Okay. Right. Now I would like to have define some symbols. Let's say this 1 volt here is VP for primary. This 1000 turns here is say NP. So NP is 1000. Now suppose that the number of turns here is say 500. Suppose that I have 500 turns here. Okay, and that's the or let's say I represent this by NS for the number of turns in the secondary coil, and suppose that the voltage output here is V S for secondary. Okay, now let me now try to calculate Vs. In order to do that, let me refresh, just quickly review the calculation I did in the last video for the Vp, for the primary voltage. The way I got Vp, the way I found Vp was to say that Vp is equal to this EMF, this induced EMF. And the induced EMF is equal to the change by Faraday's law, change in flux over time taken, and that in turn is equal to there's the number of turns, NP, 1000 turns. So that in turn is equal to 1000 times change in flux from 0 to 0.001 Tesla times cross-sectional area, which is 0.001 meters squared, divided by the time taken, which is 0.001 second, and we got 1 volt. Okay, so that's what we got. So this is the Vp. I can do that. I can do follow very similar steps for the Vs. Let's try that. Vs okay, this time the number of turns will be Ns, which is 500 turns instead of 1000 turns. Yes. Now the change in flux is exactly the same because the secondary coil coils around the primary coil, and they both coil around the same 0.001 Tesla, which spreads over this 10 cm squared of cross-sectional area over the time t. So the delta phi over delta t part is exactly the same as that. The only difference is the ns. So I can just go through this calculation, but you can already see, alright, that because delta t, delta phi are the same, NP, NS is 500, is half of NP, So clearly my answer must be half of 1 volt. Okay, so let me write it out anyway. So NS is 500 times delta phi flux change from 0 is 0.001 Tesla times cross-sectional area 0.001 meters squared over time taken is 0.001 second. So as you can see, exactly the same number, same numbers. Only difference is that 1000 turns is now 500 turns. So calculate this and we'll get 0.5 volts. Now, so the calculation is fairly straightforward, but what I'd like to point out is this. If you look at this relation between the primary voltage here and the turns number and the flux change, and if you look at this relation between the output voltage, the secondary voltage, and its turn number and the flux change, you see that in these two expressions, the flux change over time is the same, for the simple reason that both coils enclose the same flux, which of course changes over the same time t. Therefore, what we can do is this. We can take this equation, we can simply take this equation and divide by this equation. Just take this equation and divide by this equation, then the left side will give us, if I take this and I divide by this, we would get on the left side Vp over Vs, and we would get on the right side the phi and the t will cancel with the phi and the t here, so we are left with Np over Ns. And this is how we get our transformer equation. Now, one last thing that I should mention is that in this example, I've used a voltage which is fixed, and as the voltage is applied, the current increases. Right, so I've considered this example in which I have fixed voltage and an increasing current with a primary coil of 0 ohm resistance. Now, in general, meaning it's possible to also think of other examples in which instead of fixed voltage, I have a changing voltage here. So if I have a changing voltage, we'll find that we can still apply this same reasoning, except that we don't apply this idea for a fixed time of 0.001 second. We can think of maybe a very short time interval, or we can still think of 0.001 second. That seems quite short. So we can think that during the first 0.001 second, during the first time interval, I have a certain voltage. And maybe in the next time interval, the 1 volt changes to say 1.2 volts, and then I can still apply those two equations for the next time interval. And in the next time interval, still the voltage can change some more. So the voltage can keep changing with every time interval, and in that way, the same formula can continue to apply, right? Time interval after time interval. And if we imagine that the time interval is really short, then we can apply this formula to a voltage that changes in any way over time.